Okay. Yeah. Right, so this is a review of lecture 15, which is on molecular shape and polarity. So, in terms of molecular shape, thus far, we've mostly been working with Lewis dot diagrams because they help demonstrate covalent bonds and how those are formed between atoms. And we've also seen a few images, such as this one here to the right, which are three-dimensional, and they model, it's called a ball and stick model. This type of model represents a molecule, obviously in 3 dimensions. But up until this point, we have not been working with molecules in that way. And so the question is, how do we get from this diagram on the left of H2O to this diagram on the right? Obviously, there are going to be different atoms in there, but how would we model this H2O in a 3-dimensional space, like our atom on the right is modeled in a 3-dimensional space? So let's consider this molecule here on the left. This is called methane. The molecular formula is CH4, and this, if we were to draw a Lewis dot diagram, this is what it would look like here on the left. Now, we know from various studies that the actual shape that we see in the world of methane is much more like the shape here on the right. It looks almost like a pyramid, with these two, with the dashed line and the more solid thick line in the front representing 3-dimensional space, of a hydrogen atom being behind the carbon atom and one being more in front. So what's the difference between these two pictures? Well, the main difference, the key difference, is bond angles. So in this image here on the left, it looks like that's about a 90-degree angle between all of these atoms, but on the right, it looks quite different. So our textbook defines bond angles as the angle in degrees defined by lines joining the centers of two atoms to a third atom to which they are chemically bonded. So it's talking about this, this angle right here. The angle between these bonds and these bonds and these and those. So how is it that we can figure out what these bond angles are? Okay, well, it turns out that the Lewis structure here on the left is not necessarily a different shape than this than we have here on the right. It's the same molecule, CH4. So we would like to know, how can we model that based on our current knowledge? Well, one way we can do that is through valence shell electron pair repulsion theory. Now this is a model predicting the arrangement of valence electron pairs around a central atom that minimizes their mutual repulsion to produce the lowest energy orientations. So, and that's a textbook definition. Basically what this means is that electron pairs we know that they're all negatively charged. And so because particles that are charged similarly tend to repel each other, electron pairs tend to repel one another. They want to be as far away from one another as possible. Now, Earth wants to expend as little energy as possible, just in general. That's a common thing to find in the study of chemistry, that little energy is favored over large amounts of energy. And so keeping these electron pairs spread out helps with that. So how do we use this theory via CPR to determine a molecule's geometry? Well, this is what the process looks like. First thing you're going to do when you have a molecule is you're going to count the total valence electrons in the molecule. You're going to add the valence electrons at each atom in the molecule. So for example, if you had CO, if that were your molecular formula, then you know that there are 4 valence electrons in carbon, 6 in oxygen, so you have 4 plus 6 equals 10 total valence electrons in that molecule. The second step is going to be to determine the Lewis structure of the molecule, and we already know how to do that. Just using, the number of valence electrons we determined in step 1. Step 3 is to count the number of electron pairs around the central atom, and to add that to the number of atoms to which the central atom is bonded. That value is called the steric number. So the steric number you can determine just by counting how many electron pairs you have, and how many atoms your central atom is bonded to. Or excuse me, how many electron pairs your central atom has, plus how many atoms the central atom is bonded to. So if we take a look here at this chart on the left, we can see that for a steric number of 2, you have your central atom denoted by the letter E, and then you have 2 atoms that are bonded to it. For a steric number of 3, you can either have 3 atoms bonded to your central atom denoted by E, or you can have an electron pair and 2 atoms. A steric number of 4 could include 4 atoms bonded to the central atom, or it could have 3 atoms bonded to the central atom with 1 lone electron pair, or it could have 2 lone electron pairs and 2 atoms bonded to the central atom. There's a similar process or a pattern for a steric number of 5, where you can have 5, 4, 3, or 2 atoms with 0, 1, 2, or 3 lone electron pairs, respectively. And for a steric number of 6, you can have 6 atoms, 5 atoms, 4 atoms, 3 atoms, or 2 atoms. And then corresponding with those, you would have 0 electron pairs, 1, 2, 3, or 4 lone electron pairs, respectively. Now notice that as we go throughout this chart, there are always at least 2 electrons that are bonded to that central atom. Okay, so now that we know a little bit more about steric numbers, you can use the steric number of your molecule that you determined from the Lewis dot structure to determine the electron geometry of the molecule. Now, electron geometry is what's determined by just the steric number. It has little to do with whether or not there are 2 atoms and 1 lone pair or 3 atoms. If we're looking at a steric number of 3, then this trigonal planar and this bent or angular molecule, both of these molecules will have the same electron geometry. And then step 5 is determining your molecular geometry. So at this point, we have the Lewis structure, we know the electron geometry, and we would like to find the molecular geometry. So in order to do this, all you're going to do is you're going to look at your steric number, go down on the chart to figure out, which base electron geometry you're dealing with. And then you're going to pay attention to how many of those things that you counted for the steric number, how many of them are atoms and how many of them are electron pairs. For example, if you had a steric number of 5, then your electron geometry will be trigonal bipyramid. And if you had, let's say, 4 atoms and 1 lone electron pair, then you look across here and you look for which of these has 1 electron pair. It looks like this one. So you know that the molecular geometry of that molecule will be sawhorse or seesaw. Okay, so let's practice this. So let's determine the electron geometry and molecular geometry of this molecule. It has xenon and 4 atoms of fluorine in it. So the first step in this process is to count all of the valence electrons. So we know that xenon is a noble gas, so it has 8 valence electrons. We know that fluorine is a halogen, so it has 7 valence electrons. So we do 8 plus 7 times 4 because there are 4 atoms of fluorine in this molecule. So we know that in total, 28 plus 8 equals 36 valence electrons. Okay, so now you're going to do your Lewis dot structure. We put xenon in the middle. And we know that there will at least be single bonds. And then we can look at, okay, so if we were to use this so far, we have inherent electron pairs here. These are not perfectly symmetrical, that's okay. So if we have 8 electrons plus 8 plus 8 plus 8, then we have a total of 32 electrons, and we actually have 36 available. And because xenon is quite far down on the periodic table, we know that it is capable of expanding its octet. So we know that it can have, let's see, 2, 4, 6, 8, 10, 12 valence electrons here. Okay, so now we have our Lewis dot structure. So now we're just going to get the steric number, like we were talking about before. So the steric number, which is often denoted Sn, is going to be however many lone electron pair, not lone electron pairs, how many electron pairs plus the number of atoms to which the central atom is bonded. So we see here that there are 2 electron pairs on xenon, and there are 4 fluorines bonded to it. So we know that it has a steric number of 6. So now we can look back at our chart, or I'm actually not going to look back at that because I already know that a steric number of 6, you might remember, corresponds to an electron geometry of octahedral. And let's see, the molecular geometry is where we take into account how many electron pairs there are and how many atoms there are within this steric number of 6. And we see, okay, 2 of them are electron pairs, 4 of them are atoms. So you go and look on the chart and you look for the one with 4 atoms and 2 not lone electron pairs, just 2 electron pairs. So when you look at the chart, you see that it comes up with a square planar molecular geometry. What exactly that looks like, let's see if I can draw. So it looks like you have your xenon here in the middle, and then it's square planar, which means this is in one horizontal plane in the shape of a square. And then above and below that plane are the electron pairs. So this is actually what that molecule is going to look like. Okay, so we have determined the electron geometry and molecular geometry of this molecule. Now, do you remember those bond angles from earlier that we were talking about? You might be wondering how we determine those bond angles. We might know that we have a square planar molecular geometry for that last molecule, but what does that mean about the specific angles between those atoms? Well, it's also nice to have that chart we were looking at earlier because it does tell you those values. So over time, you'll start to memorize them, and you will quickly understand that, just as we were talking earlier, throughout this VSEPR theory, the electron pairs and the atoms are really trying to be as far apart as possible. And so that, along with just some knowledge about angles in general, will help you recognize, if you can't memorize that chart, what the molecular geometries will be, what the bond angles will be based on the molecular geometries. Okay, so let's practice one of those. So if we're to do the bond angles for CO2, we again begin by counting how many valence electrons we have. So we know that carbon has 4 valence electrons, oxygen has 6, and there are 2 atoms of oxygen here. So we're going to have 4 plus 12, 16 valence electrons in this atom. And now we can do our Lewis dot structure. We know that oxygen tends to double bond with things. And even if you don't know that, you know that carbon is going to want four sets of electrons. And so you can just mess around with this for a little bit, and you'll see that they are, in fact, double bonds between the carbon and oxygen. Then we know we have 2, 4, 6, 8 valence electrons, and we need 8 more. We know that these are. Okay. So now we have our Lewis dot structure. We can look at the steric number. Now the steric number is again defined as the number of electron pairs on a central atom plus the number of atoms that are bonded to that central atom. So here we have 0 electron pairs on carbon. We have 2 atoms bonded to it, which makes for a steric number of 2. Then a corresponding electron geometry. And when you look at the chart, you see that that is in fact linear. And then the molecular geometry for a steric number of 2, there's only one option, which is linear. Now, what does this mean about bond angles? Because that's what we're looking for here, right? Is bond angles. Well, if you look back at that chart there, you'll see, or you can just look at the fact that this is linear. So if we were to make a ball and stick model, this is the carbon, this is the oxygen, these are the oxygens. And so we see that, it's 360 degrees around, which means halfway around is 180 degrees. And since these bonds are straight, you can see that there are 180-degree bond angles. Okay, let's move on. Actually, just a quick note on this particular molecule. So we were just looking at CO2's Lewis dot structure. We see that it has double bonds, and some students might mix this up and say, okay, it has a steric number of 4 because there are 4 bonds. But remember that the steric number is only affected by the number of atoms bonded to the central atom and by the number of electron pairs. There are 0 electron pairs and there are only 2 atoms bonded to carbon, so the steric number is 2. So the fact that these are double bonds doesn't affect the steric number specifically. Another note is that in this case, the electron geometry was linear, as was the molecular geometry, but that's not always the case. And, to recognize that, we can just think back to the xenon example, in which the electron geometry was octahedral and molecular geometry was square planar. Okay, let's talk about some polar molecules. So, if we were to draw out H2O, we would see that you have your one hydrogen, or your, excuse me, you have your one oxygen with your 2 hydrogens. We know that oxygen has 6, hydrogen both have 1 valence electron, so there's a total of 8 single bonds there. So this must be the dot structure. So we look at the steric number for this, and we see, okay, 2 atoms are bonded and 2 electron pairs are left on the central atom, which is oxygen. So that's 4. And then we look at the chart, we see that that is a tetrahedral electron geometry. And, okay, so we have a molecular geometry that is also known as angular. Okay, and then we can identify the bond angle as less than 109.5 for that particular molecule. So this is a really interesting atom or molecule here. So let's look at how the electrons are distributed in this. So we know that electrons have negative charges. And so if there are electron pairs, I'll just draw them here, as was on our Lewis dot structure. We know that electrons are negatively charged. So if there are lone pairs up here, then how is the overall negative charge distributed throughout this molecule? More of it is up here, as well as the fact that oxygen, and that on top of the fact that oxygen is a more electronegative atom, creates a partial negative charge up here. And that also creates a partial positive charge on the hydrogen. So this means that, sometimes we call a partial positive charge or a partial negative charge poles. So we call this up here at the top, we call this a negative pole, and the bottom is a positive pole on both hydrogen atoms. So to determine if a molecule has a dipole moment, which is just another way to say is polar, if the molecule is polar, you draw the Lewis structure, you determine the electron geometry and molecular geometry like we already did for water, and then you compare the electronegativities of your atoms, so oxygen versus hydrogen. If they're equal, then you're not going to have a polar molecule. But if they're not equal, then it's a little bit more tricky. So you can denote a thing just about specific things for writing these poles. You can denote a partial negative charge like this, or you can draw an arrow with the positive end, or with this plus end, positive end of your pole. Okay. So we can do set. So let's practice with the molecule CO. If we can determine any sort of polarity here. So okay, so if we do this molecule, we can do the list dot structure and see that this is what it ends up looking like. I can write this out real quick. It's 4 valence electrons, carbon 6, and oxygen. So you end up with 10 valence electrons. And many of those have to be shared between carbon and oxygen. So you end up with a triple bond and these 2 valence pairs. Now note that this is, it looks to be symmetrical at this point, with 2 electron pairs on the right, 1 electron pair on the right, 1 electron pair on the left, 3 bonds in the middle. However, this is still a polar molecule, and that is because we refer to the electronegativities, which are just inherent they're just inherent properties of these atoms. So if you look at the electronegativities of oxygen, you see that it's 3.44. Carbon is 2.55. So clearly the electronegativity of oxygen is greater than that of carbon. And electronegativity is the ability of electrons. And so therefore more electrons are going to be concentrated on this side, the right side of this molecule. And so because of that, we can write that the positive end molecule is there, the negative end of the molecule is there. So therefore, this is a polar molecule that has a dipole. Okay, I hope that was helpful. And yeah, thank you for learning with me today. Appreciate it.